Okay, here we are, 5.4, day number 2, the fundamental theorem of calculus, part 2. First page here is going to be a little bit of pattern recognition. So the first thing that I want you to do is to find the integral, okay, just this piece here. Find the integral of that and evaluate it from 1 to x. Don't worry about the dx before it yet. I'm going to do that off camera and we'll compare ours. Okay, so I found the antiderivative right here. I'm going to use the first fundamental theorem of calculus to evaluate. This is big F, right? So this with x plugged in red, and then with 1 inputted in blue. Now why in the world would I just leave that as a constant and not evaluate it all the way through? The reason why is I'm about to take the derivative of both of these. If I take the derivative of a constant, that's always equal to 0, so it won't matter. So if I take the derivative of the red piece here, that would be 4x cubed over 4 plus 3 times 2x squared over 3 plus 4. The 4's cancel here, the 3's cancel here, and it looks like I get x cubed plus 2x squared plus 4. Does that look familiar? X cubed plus 2x squared plus 4. T cubed plus 2t squared plus 4. Not coincidental. Let's look at another example here. In example 2, whoa, double lightsabers, where'd you come from? Okay, let's do it again. Okay, so again, I want you to do just this piece right here. Leave the d dx for a few minutes from now. Okay, I get the same antiderivative, however, the limit of integration, the upper limit of integration, is now x squared instead of x. So when you evaluate that, I want you to plug it in, but I want you to keep x squared as is. I don't want you to distribute any exponents, I just want you to keep it in general terms. You'll see what I mean in a second here. Okay, so I've plugged in x squared. I have not simplified this, I have not simplified this, I have not done anything else. Alright, again, I didn't go any further with the constant piece. Plugging in a 1, that's just going to go to 0 as I take the derivative. So now I'm going to take the derivative. Let's see what happens. I would get 4 times x squared cubed over 4 plus 3 times 2 times x squared squared over 3 plus 4. Now you might be thinking, well, what about the x squared? Okay, so if I were to do a derivative in this case, this would be a chain rule example. Alright, each of these would have tagging along with them the derivative of x squared, which is 2x. So let's do a little bit of cleaning up here. 4's will cancel, 3's will cancel, etc. Our function would be x squared cubed plus 2x squared squared plus 4 all times 2x. Okay, so let's make a little observation here and see this pattern. What did I cube this time? What did I take 2 times and then square? Okay, I cubed x squared and I took x squared squared. So what am I subbing in for t in this case? Well, again, it's this item, this upper limit. However, when this upper limit is not just x, or actually not just x, if there is a derivative, if I took the derivative of this and it was something other than 1, I have to then multiply by that value at the very end. Okay, so in general terms, if I have the derivative of the integral from some constant to, let's say, g of x, right, some function, f of t dt. That will be equal to f of g of x times the derivative of g of x. All right, that's going to hold true every time. Every time. Let's try one. Oh, nice. The derivative of this x is 1. Therefore, this will be pretty easy. This will be e to the x times cosine of x times the derivative of x, which is 1. We're done. Okay, how about this one? Well, the derivative of this is 3x squared. So what I'm going to do is I'm going to input x cubed everywhere I see a t. So I have 1 over the square root of x cubed squared plus x cubed times the derivative of that upper limit, which is 3x squared. I'll do a little bit of simplifying here. In the numerator, I'll have 3x squared. In the denominator, I'll have the square root of x to the 6th plus x cubed. That would be complete. All right, so here's what the fundamental theorem part 2 tells us. If f is continuous on this closed interval a to b, then the area function, remember back a ways when we were doing area functions and it was a pain in the neck? Well, now that area function is pretty easy. It's the integral from some constant to x of f of t dt. All right, it's continuous, and this area function is continuous on a to b and differentiable on the open interval a to b. The area function satisfies that the derivative of the area function is the function itself, or equivalently, you see this notation. So up until right now in these notes, we've been finding the derivative of the area function. This means the area function of f is an antiderivative of f on a to b. Okay, so let's look at another example here. Will the derivative of that thing be 1? The answer to that is no. So if I took the derivative of this integral, again, this constant doesn't matter at all. What I'm going to get is the sine of the cosine of x times the derivative of this, which is negative sine of x. Okay, so negative sine of x. So I know the derivative of the area function is equal to this thing. I could clean it up a little bit. I'm going to bring that negative out in front. And just clean that up, make it look nice. Alright, that would be done. Alright, here's a funky one. This one's going to take a little bit more space, so I'm going to make some room. Alright, I'm going to kind of blow this up a little bit, and you'll understand in a moment. Okay, this lower limit is not a constant, so I have to make it a constant. So here's what I'm going to do. I'm going to take the derivative in a moment of two integrals. I'm going to take an integral from sine of x up to some constant between sine of x and cosine of x of u squared du. And I'm going to add that to the integral from that value a up to that upper limit cosine of x of u squared du. Alright, now up until this point we've always had this constant, right? This constant right here, down here. Well, I am allowed to do the following. Alright, using properties of integrals, I can switch those limits, but what I must do is I must change the sign of the area that is then an output from there. And then I don't change anything with the second integral. And I simply do some integration on that, or some the derivative of those. I'm going to do that off camera and I'll come back and we'll see how we did. Okay, so let's see what we did here. I noticed that the derivative of this is not 1 and nor is the derivative of that, so I'm going to have to do a chain rule work here, but I'm going to plug sine of x in for u, so I get sine of x squared. Okay, don't forget this negative. And then I have to take the derivative of sine of x, which is cosine of x. Over here, again, these constants here won't matter, but I plug in cosine of x for u, so I get cosine x squared, and the derivative of cosine is negative sine. So let's clean it up here and get the derivative of the area function. That would be equal to negative sine squared x, means the same thing, just a different notation, times cosine x. I'm going to bring this negative out in front and call that cosine squared x times sine x. It looks like you might be able to simplify them, but no, you can't. Alright, so at that point we'd be complete on that problem. Alright, some properties of integrals here, and some stuff to do with even odd functions and their integrals. This is some stuff that we can cover in class or on the side if you'd like, but you should be aware of these properties. So go ahead and make yourself familiar with those and ask questions when needed. Alright, so let's do a couple homework problems. Okay, so I have taken the derivative of big F of x. The derivative of that, of course, would be the square root of x cubed plus 1. So f prime of 2 would be an input of 2 here, which would give me 2 cubed, which is 8, plus 1. Square root of 9 would be 3. Okay, derivative of this integral, this is again second fundamental theorem of calculus. I'm going to go ahead and input x squared into t. So I'll get sine of x squared cubed times the derivative of that upper limit, okay, which is 2x. So I'm going to bring that 2x out in front and simplify the inside here. Looks like I get this. Ah, yes. Hello, E. Alright, number 92. Looks like it's from 2003. Let g be the function given by that between -1 and 3. On which of the following intervals is g decreasing? Ooh, so I want to know where g prime is less than 0. Less than or equal to, I'm sorry, less than or equal to 0. Alright, so g prime would be fundamental theorem, derivative of that is 1, so I just have to do a direct substitution. I want to know where sine of x squared is less than or equal to 0. You're going to want to consult your calculator. So type this in for y1 and go ahead and find out where that'd be less than or equal to 0. It looks like using my calculator, this comes out to be the interval in which that is true. Oh, 2008, do I love you. Alright. The graph of the function f shown above has horizontal tangents at x equals 2 and x equals 5. Let g be the function, blah, blah, blah. For what values of x does the graph of g have a point of inflection? Okay, so point of inflection, f double prime has to equal 0, and f double prime has to change signs. Okay, so how would I find f double prime? Or in this case, that should be g double prime and g double prime. So, well, first we got to find g prime of x. G prime of x would be the fundamental theorem of calculus here, which if I do that, would be f of x. Okay, so the derivative is the output on this graph. So g double prime would actually be the derivative of that graph, or the slope of that graph. So where would the derivative be equal to 0, right? That's what I'm looking for here. Even though I'm looking for the second derivative, I'm looking for the second derivative of g, but I'm looking for the derivative of f. So where is that 0? We were told that that's 0 here, and that's 0 here. Okay, does that derivative, the derivative of the function, change sign? Well, it looks like the slope of this is positive, then it's 0, then it's negative. That's a point of inflection. Okay, so we know 2 is a point of inflection for sure. So that eliminates E, that eliminates B. Alright, let's see if there's another one. Okay, so we've got f double prime equal to 0 also at 5. Does the slope change sign? It's negative, it's 0, it's positive. Yes, 5 would also be a point of inflection. Alright, so that eliminates A. Let's look at 4 for a minute just to make sure. This is actually a distractor. F of x equals 0. It does not mean that f prime of x equals 0 here. Therefore 4 is not, and therefore our answer would be C. Alright, so let f be the continuous function defined on -4 to 3, whose graph consisting of 3 line segments and a semicircle are centered at the origin, is given above. Let g be the function from 1 to x. So the g of x is going to accumulate area from 1 to whatever value we have for x. So let's look at g of 2 first of all. So part A, let's look at g of 2. So g of 2 would be the integral from 1 to 2 of f of t dt. So what would the area be between 1 and 2? That's what that's asking. Okay, so we got to do a little work with triangles. Okay, so it looks like this would be 1 and this would be 1/2. So the area of a triangle that's got a base of 1 and a height of 1/2, well, that area would equal 1/2 base times height. Okay, so it looks like that area, which is equal to g of 2, would equal 1/4. Alright, that's all the time I'm going to have for today. We can get to more of this later when we have some time together in class. That is 5.4, day number 2, Fundamental Theorem of Calculus, Part 2.